Hello, this is Mr. Warwick. I'm here to talk to you about lesson 11.4, area of regular polygons and composite figures. This is the fourth lesson from chapter 11. It's got a lot to say in some parts and not much else to say in others, so let's just kind of dive right in. The first couple terms are not well defined in the book, so I've kind of put a definition up here for you. That's the center of a regular polygon. It's the physical center, the intersection of all the radii, and then the radius of a regular polygon is a line from the center to the vertex. Really, it should be each vertex. So if I've got a center here that's the physical center of this pentagon, then I've got a radius that goes out to each of the vertices of that. Makes me a nice little Chrysler logo there. It is mentioned in the book, so this is worth noting. It would be the same as for the circumscribed circle. So if we were to put a circle around, circumscribed, meaning it touches all of the outer points of this pentagon here, then the radius of this pentagon to those vertices where it would touch that circle would be the exact same as the radius for that circle. Okay? And then the center of that circle would be where the center of that figure is. Be it a hexagon, an octagon, whatever it is, that's what we are dealing with. The central angles, which would be, again, on this one, this angle right here, all we have to do is understand that that's going to be a circle, and we divide it by n, where n is the number of sides. If we have a hexagon, that's 360 divided by 6. Each angle there in the middle is a 60-degree angle. If we have an octagon, we're looking at a stop sign. If we were to split it into all these triangles like this with the radii, then 360 divided by 8, it'd give us 45. The next term that you need to make sure you have defined is the apothem. This one's very important for what we're doing. The apothem is a line perpendicular to the side from the center. So if you can imagine this being cut into triangles, then this dotted line coming down, that would be a 90-degree angle here. The height of my triangle that I have cut this is my apothem. Okay? It's essentially like a height for one of these polygons, but it's not the height of the whole thing, because that's not how we determine area of it. The area of a regular polygon, which if you remember back from our definitions, regular means it's exactly the same on each same side. On each one of these sides around the outside, it has the exact same measure. We would divide this into triangles to find that area. So the area, as it's listed in the book, is either 1/2 of the apothem times the side times the number of sides, or 1/2 A S N, or you can think of it the other way they put it is the area is equal to 1/2 of the apothem times the perimeter, which the side times the number of sides would give you that perimeter. So it's the same measurement there. When you're multiplying, it doesn't actually matter what you are looking at. Or this is always right here. It's not one that comes from the book. This is how I've always thought of it when I work these problems. I find the area of one of these triangles that I have divided my shape into. Okay, I get that triangle area and multiply it by the number of triangles that I have. In this case, it's a pentagon. It's still going to be 5 triangles. A hexagon would cut into 6, an octagon into 8, a septagon into 7, a dodecagon, I believe, is 12. So you'd cut it into 12 triangles. You'd find the area of that triangle, and you'd multiply it out. You might check me on the definitions on dodecagon. The other thing that the book has is composite figures, and it really has you doing more composite figures, which means it's a trapezoid with a semicircle on top, or it's 2 triangles at either end of a parallelogram. Something where it's kind of divided up. It can be even some 3D shapes where you're doing some surface area on some 3-dimensional shapes to make it just a little bit more difficult for you. But really, all you do for composite figures is you add the areas of the non-overlapping parts. So if I have a hexagon, and it's a very obvious hexagon that they want me to find the area of but then on each part of that hexagon is a semicircular flower shape. And I'm going to find the area of the whole thing. What I'm going to do is I'm going to use my central angles. I'm going to determine each of these triangles. I'm going to multiply that by 6. I'm going to determine the area of this semicircle, and I'm going to figure out 6 of those semicircles, and I'm going to put the whole thing together. It's a process that hopefully by now, with all of the work that we've done on area, the different lessons, that it just really catches on very fast, and you should be able to get it very easily. If there's something about this that doesn't make sense, if I need to kind of go back over this area of a regular polygon and the dividing into triangles, when we get to class, just make sure to raise your hand or come in during tutorials. I'll explain it to you, and we'll see you then.